Hi, my name is Naina Coley, and for my Case Connections video, I have chosen to do Case 1 and 4. Starting with Case 1. The first part of the question asks all the ways in which pyruvate kinase is regulated in the cell under normal conditions. The question tells us a little bit of background on pyruvate kinase, even though this is a crucial step in glycolysis that we learned about earlier in this unit. As it states, it is an ATP generating step of glycolysis where phosphoenolpyruvate is converted to pyruvate. In the glycolysis pathway shown here in an image from our textbook, we can see that it is the last step of the reaction. The flow diagram also gives us a visual representation indicating that pyruvate kinase is one of three regulating steps of glycolysis, which can be indicated by their irreversible mechanism shown by the one-sided arrows. Having this be an irreversible reaction is critical because it prevents its reactant, phosphoenolpyruvate, from building up due to the equilibrium reactions before it. So if there happens to be a lot of phosphoenolpyruvate, the step before can shift towards phosphoglycerate according to Le Chatelier's principle. So when we talk about hormones or substrates that regulate an enzyme, we need to look at the big picture of the reactions that this enzyme can affect. Starting off with the immediate steps, since pyruvate kinase makes ATP from ADP, ADP is an activator of this enzyme and ATP is an inhibitor of this step. Another activator that is present in glycolysis is fructose 1,6-bisphosphate. This is an activator because if this is present, then most likely glycolysis is already occurring, and since pyruvate kinase is the last step in glycolysis, it needs to be activated in order to complete the pathway. Now looking back a bit further at why glycolysis may need to be inhibited or activated can help in determining some other regulators of pyruvate kinase. The main hormonal regulator is insulin. Insulin facilitates the uptake of glucose from the blood into the cell when there is an abundance of glucose in the blood. This uptake of glucose increases the need for it to be broken down, meaning it must go through glycolysis. As one of the regulators of glycolysis, pyruvate kinase is activated. The hormonal inhibitor would be glucagon-mediated phosphorylation. Glucagon is released when there are low levels of glucose in the blood. As a result, we do not want to be breaking down any more glucose. Instead, we want to have the liver break down glycogen and release more glucose into the blood. Alanine is another inhibitor that indicates gluconeogenesis needs to occur. Again, when gluconeogenesis needs to occur, we do not want to have glycolysis going on so that the glucose that is just being made will not be immediately broken down. For this reason, pyruvate kinase will not need to be activated. Now addressing part 2 of the question, which explains a bit about the pyruvate kinase type M2 and how it is ineffective in promoting glycolysis, which seems counterintuitive for a glycolytic tissue. The reason these cancer cells are slowing down the pyruvate kinase step is so that pyruvate is not the only product that is being formed in this reaction. For cancer cells to thrive, they need other organelles to be made or other products that can keep their cells growing. These cells have consequently cleverly developed a way to meet their needs using the substrates present to their advantage. Interestingly enough, if we look back at the pathway for glycolysis, one of the precursors is 3-phosphoglycerate. This precursor can be used to make lipids and amino acids such as serine and glycerine. So when the substrate builds up, due to the slowing down of pyruvate kinase, some of this 3-phosphoglycerate can be diverted to lipid synthesis and other pathways such as the pentose phosphate pathway. This makes it beneficial to these cancer cells to have this slow down mechanism of pyruvate kinase. Now on to case 4, where we are given a case study about a patient and trying to deduce their diagnosis. We are given that this is a 2-month-old female. She is jittery after breastfeeding. She has only had breast milk. She is lethargic. She has low blood glucose levels, but these levels increase after breastfeeding. She has an enlarged liver, and when epinephrine is administered, there is no increase in blood glucose, but there is an increase in blood lactate. There are 4 options given to us for what the possible diagnosis could be. However, let us try and see if we can determine a general idea of what may be going on before jumping straight to the answer choices. So this baby is clearly able to break down lactose and then break down the glucose. An enlarged liver, however, indicates that there's something that is not being broken down correctly and that this buildup is causing the hepatomegaly. The lethargic state of the baby and the jittery spells several hours after breastfeeding points multiple signs that glycogen breakdown is not occurring properly. Additionally, the administration of epinephrine will inhibit glycolysis in the liver, trying to increase blood glucose levels by signaling to the liver to convert stored glycogen to glucose. However, when epinephrine was given to the baby, there was no increase in blood glucose, but there was an increase in blood lactate. The increase in blood lactate is due to the anaerobic glycolysis that is still taking place to create at least something that the body can use for energy. This all points us to some problem that is happening with glycogen. Now let us revisit the answer choices to see if anything matches this. Hereditary fructose intolerance is the result of no aldolase B. Aldolase B cleaves fructose 1-phosphate in both the pentose phosphate pathway and glycolysis. Although some of the symptoms, such as low blood glucose levels and enlarged liver, are consistent with this patient, this disease prevents the breakdown of fructose, and the baby, in this stage of her life, has only been exposed to breast milk, which contains lactose. This disease is therefore most likely not what the baby is experiencing because it relates so much to fructose, which is not even in the baby's diet. Glucose 6-phosphate dehydrogenase deficiency presents problems in the pentose phosphate pathway because it is the main regulatory enzyme in the oxidative part of the pentose phosphate pathway. This deficiency leads to oxidative stress and leads to the hemolysis of red blood cells. This condition can easily be ruled out as there are no symptoms of low red blood cell activity. Additionally, this condition is almost exclusively found in males because of its gene location on the X chromosome, which does not fit the characteristics of the baby girl. Galactosemia is the inability to metabolize galactose, usually due to a transferase deficiency. The symptoms of galactosemia include mental deterioration, lethargy, enlarged liver, and low blood glucose levels. When babies take in lactose, it is broken down into glucose and galactose. However, if there is a buildup of galactose, then it is unable to use glucose to produce energy. There are many ways in which this disease seems consistent with the baby's symptoms. However, the last thing that was mentioned was the administration of epinephrine. Ultimately, if epinephrine was administered to a baby with galactosemia, there should be no reason why other forms of stored glucose could not release glucose into the blood. This is therefore inconsistent with what the baby is experiencing and makes it likely that the baby does not have galactosemia. Furthermore, the main symptom of galactosemia is jaundice, and this is not observed in the patient. Glycogen storage disease is a disease that occurs when glycogen cannot be broken down. This leads to a buildup of glycogen in the liver, which explains the hepatomegaly. The buildup of glycogen can then not be turned into glucose when the body needs it. As a result, glucose is being broken down perfectly fine and everything else is working. There are just issues in releasing the glucose into the bloodstream during fasted states. This explains the hypoglycemia because not enough glucose is being sent in the blood. Von Gierke's disease is the most common glycogen storage disease, and this is where there is a glucose 6-phosphatase deficiency, which catalyzes the release of glucose into the bloodstream by the liver. This deficiency increases the amount of glycogen in the liver and is unable to increase blood glucose levels in response to glucagon and epinephrine. This addresses all the aspects of the patient's symptoms and is most likely the diagnosis of the 2-month-old girl. These are the slides for glycogen storage disease, and these are my references. Thank you.